This is 3.4 part 2. We are now looking at composition of functions. So composition of functions, and then we also want to get the domain. If f and g are functions, then the composite function or composition of g and f is defined by this. So be careful, this symbol here, that means composition, not multiplication. So see how it's an open dot? That means composition. Which is the same thing as saying, so if you have the g first and the f second, you're actually doing g of f of x. So you are actually plugging in the function f into the function g. Okay, so this means the same thing, g of f of x. The domain of g of f is a set of all numbers x in the domain of f, so it has to be first in the domain of f, such that f of x is also in the domain of g. So whatever you're plugging in to the function g, well, we need to be in the domain of g as well. So what that comes down to, if we just want to simplify that for ourselves, is the domain is going to be the intersection of the domain of f the domain of f of x and the domain of g of f of x. So that is the domain of the input function the function you're plugging in, and then the domain of the composite function. So you need to check both of those, and then it's going to be the intersection of those two domains. All right, so let's see an example. So given that f of x equals 6 divided by x minus 3, and g of x equals 1 divided by x, find each of the following. A, f of g of x and its domain. So remember, that's the same thing as saying f of g of x. So you are plugging in the function g into the function f. Well, here's the function f. F of x equals 6 over x minus 3, but instead of writing x in the denominator, I need to write g of x. Okay, so all I did there was replace this x with g of x, because that's what we have here in parentheses. Well, what is g of x? G of x here is 1 over x, so I'm going to replace g of x with 1 over x. And there's the function. Now I do want to simplify that. You always want to simplify your composite functions as far as you possibly can. You did learn how to do this when we looked at complex fractions. So first you need to subtract those two in the denominator, the two terms in the denominator. So to do that, we need a common denominator, and that is going to be x. So I'll multiply by x on the top and the bottom for the 3. Okay, so that's 6 over, now I can subtract those because they have the same denominator, x. So 1 minus 3x all over x. Okay, we don't want a fraction over a fraction, so let's just keep going. Remember, that's the same thing as doing 6 over 1 times x over 1 minus 3x. You're dividing a fraction by a fraction, so you can flip the bottom one up and multiply. Okay, so that comes out to 6x over 1 minus 3x. Okay, and that is the composite function. But now we need to get the domain. Okay, so like I said, you want to get the domain of the input function. So that's the domain of g of x. So your domain is going to be the domain of g of x and the intersected with, that's what that symbol means there, intersected with the domain of the composite function, which is f of g of x. Okay, so let's get the domain of g of x. For g of x, that's going to be, well, look at the function g of x right here. Denominator cannot equal 0, so x cannot equal 0 for the domain of g of x. Now the domain of the composite function, so we're looking down here, that's f of g of x. Well, the denominator can't equal 0, so 1 minus 3x cannot equal 0. That's 1 cannot equal 3x. X cannot equal dividing by 3, 1/3. So for this one, x cannot equal 1/3. So I got the domain of g of x, that was x cannot equal 0. The domain of our composite function here in the green box, that is x cannot equal 1/3. So putting those together, x cannot equal 0 or 1/3 would be the domain of our composite function. I can write that in interval notation by doing negative infinity all the way up to 0. Parentheses can't equal 0, so we're going to jump over that 0, go to 1/3. Can't equal 1/3, so we have a parentheses there as well, to infinity. So that's writing it in interval notation. It's actually easier if you write this one in set builder notation, in my opinion. So this is interval. But if we did set builder, since all we're doing is excluding two numbers, we could say the set of all x such that x does not equal 0 or 1/3. And that would be that. So I kind of like that when I'm just excluding two numbers, but you'll see interval used a lot still. All right. Now looking at b, we're doing g of f of x. So that is g parentheses f of x, plugging f of x into the function g. So let's see what the function g was. It was 1 over x. But instead of x, we are going to put f of x. So 1 over f of x. Well, f of x is 6 over x minus 3. Right? 6 over x minus 3. So in the denominator here, I'll put 6 over x minus 3. Again, we have a complex fraction, so let's simplify that. We'll flip the denominator up and multiply. That's 1 over 1 times x minus 3 over 6. And that's just x minus 3 over 6. All right, so now getting the domain, we want to get the domain of f of x and the domain of our composite function. So the domain of, I could just write d of f of x. We know we're talking about the domain of f of x. Again, looking at the denominator there, there's a fraction, so it's going to be, looking at this, x cannot equal 3. Because then you would be dividing by 0. And then the domain of g of f of x, looking at the domain of this guy at the bottom, well, the denominator is just 6. So you're saying 6 cannot equal 0. Well, 6 is never going to equal 0, so that's not an issue. The domain for this one, since there's no x in the denominator, is all real numbers. So now putting those two together, all we have to worry about is the domain of f of x. So your domain is going to be x cannot equal 3, so that's negative infinity up to 3, 3 to infinity. Writing that in interval notation. Should probably box that up here as well. The domain. Writing it in either notation. All right, next page. All right, we're going to do a little more practice on that same type of problem. Okay, so f of g of x. F, plugging in g of x. So here's g of x, 4x plus 2. We're plugging that into the square root of x. So that's the square root of g of x, just replacing the x with g of x. Well, g of x is 4x plus 2, so the square root of 4x plus 2. Okay, that's the function. I can't simplify it any more than that. Its domain. So we do have a radical here if you're looking at f of g of x. First, let's look at our input function. So the domain of g of x. That is actually, since that's a linear function, going to be all real numbers. So the domain of f of g of x. Well, we have a radical, so we have to do 4x plus 2 has to be greater than or equal to 0. So subtract the 2, divide by 4. That's negative 1/2. So x has to be greater than or equal to negative 1/2. We'll write that in interval notation. Greater than or equal to, whoops. So I'll get a square bracket on that. And this was the function. Okay, now g of f of x. So we are doing g parentheses f of x. I prefer it written like that. It's a little more clear, but they mean the same thing. Okay, so we're plugging f into g. So function g is 4x plus 2. So that's 4 times f of x plus 2, just replacing that x with f of x. F of x is the square root of x, so that's 4 square root of x plus 2. Okay, that's the composite function. Now our domain. So you will have the domain of the input function, f of x. Oops. So the input function, well, we have a radical there on f of x, so that's x needs to be greater than or equal to 0. And then your domain for g of f of x. Again, you have that radical there. X has to be greater than or equal to 0. So they actually have the same domain. So that is just x is greater than or equal to 0 for both. All right, and finally on this last example, we are going to be evaluating composite functions. So let's see what this means. The only difference here in the question is that we actually have a number instead of the variable x. So we are finding f of g of 2. That's the same thing as saying f of g of 2. Okay, so you want to start from the inside out. So I would start with finding g of 2. You want to find g of 2, and then you're going to plug that into the function f. So I'm going to start with g of 2. So that's 4 over 2 minus 1. That's 4 over 2 minus 1 is 1. So that's 4. So g of 2 is 4. So I can now replace this g of 2 with 4, with the number 4. So that's f of 4. My function f is 2x plus 1, so 2 times 4, minus 1. So that's 8 minus 1 is 7. And that's how that works. You could do it differently if you wanted to. I like to pull that g of 2 out, find that first, and then plug it in to find f of 4 like that. But you could also do, let me do it in a different color, purple. If you wanted to, you could do f of g of 2. Well, g of 2 is going to be 4 over 2 minus 1. So just leaving it composite like that. You could leave it together and solve it at the same time if you're comfortable with that. And then f of 4 is 2 times 4 minus 1, which again comes out to 7. So if you wanted to not separate it and actually solve g of 2 separately, you can do that as well. Okay, so on this one, g of f of negative 3. So I need to find f of negative 3. That's 2 times negative 3 minus 1. Negative 6 minus 1. Negative 7. Okay, so now I'm going to plug that in right here for f of negative 3. So now g of negative 7 is what I'm looking at. Right? I just replaced that f of negative 3 with negative 7. So that's 4 over negative 7 minus 1, 4 over negative 8, which reduces to negative 1/2. And that would be it. If you want to see that done the alternate method, just leaving them together, that's going to be f, right, or here, you could do g of f of negative 3, g of, well, f of negative 3, just looking at your function f, is 2 times negative 3 minus 1, which comes out to negative 7. G of negative 7 is 4 over negative 7 minus 1, which comes out to 4 over negative 8, negative 1/2. Okay, so either way, you get the same thing. If it makes more sense to you to break it apart, do it. If it makes more sense for you to keep it together, like so, then you can do it that way as well. All right, that concludes 3.4.